Hello again. In this lecture, we look at continuous random variables. So far, we've seen discrete. We looked at binomial and Bernoulli in particular. Now we look at continuous random variables. The ideas here are a little bit different. Firstly, we want to understand the concept of a continuous random variable. We're going to work here with probability density functions. In the previous case, with discrete, we have probability mass functions. Now we have probability distribution functions. We'll also look at this idea of cumulative distribution function here. We did have a look at briefly in the discrete case, but not so much in detail. We understand looking at a special uniform distribution, and we'll take a look at expectations and variances in simple cases. And we'll take a look at the mean and variance of a uniform distribution. So starting off, the idea here is this. Discrete random variables take values in some finite set. So I might have 0, 1, 2, 3, 4 up to 10 if I'm tossing a coin 10 times. Or at least a set that can be listed. Continuous take values in some interval. So here I can't list the values. I can't say how many values there are because it would be, if I'm looking at say the height of students in my class, I would say the heights lie between 1.5 meters to 2.2 meters. But I can't say exactly what values the heights take. Example here is random variable t denotes the time to the next failure of a machine. All I know is that t is bigger than or equal to 0. Now, if I'm looking at a particular value, like looking at probability one of my students is exactly 2 meters high, 2 meters tall, that'll be 0 because 2 meters is only one value in a whole continuum, one value in infinitely many values. So that'll be 0. So probability for single events or single values for continuous distributions are 0. However, if I look at this situation, probability I hit exactly the center of the dartboard. This is 1 point out of infinitely many. So this probability is also 0. However, when I do throw the dartboard, I do hit something in the dartboard. So probability is 0 there for a single point. But this is a little bit more complex than you might think it is. But for the moment, all we want to understand here is probability for a single value for continuous distributions is 0. Continuous distributions don't have probability mass functions. Instead, they have what we call probability density functions. And we evaluate probabilities for intervals, not for single values, because probabilities for single values are 0. So here is the concept of a density function. There are two things that we require here. A function, a probability density function, has two things. One is it must always be bigger than or equal to 0. It can't be negative. And the second is the total area under the graph is equal to 1. The third thing is probabilities for intervals are given by the area under the graph between those intervals. So if I've got something here that's continuous and looks like this, for example, then the first thing is, as I say, it must be positive, which must be bigger than or equal to 0, which it is. The total area here must be equal to 1. And if I want probability that this random variable lies between, say, points A and B, I look at the area under the probability density function between those particular values. So that area here is probability A less than or equal to X less than or equal to B. That's how these things work, simply by finding areas. Here's an example. So here's the PDF we're looking at. X is the random variable, and this is the PDF. Now there's a typo in here that I want to fix. It should actually be x plus 1 over here. And negative x plus 1. So, to sketch this, note these are straight lines. I will look at just the endpoints. To define a line requires just 2 points. So there's my values of x, and there's my probability density function. Notice previously for probability mass function we used p in this sense. Now you change that to f for a function. So here, when x is negative 1, I get 0, so y is 0 over here somewhere. when x is 0, this is equal to 1. So this is a straight line. Y equals 1 is over here somewhere. A straight line that looks like that. That point here is when x is equal to -1, I get 0. When x is equal to 0, I get 1. For this second line, the same thing. I take a look at when x is 0, I get 1, which is this point here. And when x is 1, this is 0. So that's going to go down to 0 over there. This is equal to 0 when x is equal to 1. It's a triangular distribution. To show this is a PDF, I've got to find the total area here. First of all, this is always bigger than or equal to 0. So part A here, fx is bigger than or equal to 0, which is the first condition required. And the second part here is total area. Now this is a triangle, and so it's half base times height. So there is a half. The base is 1, 1 is too long, and the height is 1. That comes to 1. So F is a PDF. The second part asks to work out some probabilities. The first is probability x lies between 0 and 1 over here. So I don't need to do much work for this. I'll go back to the PDF here. There is 0, so what I'm after here is this probability here, this area. I can work it out actually. It's a triangle. Half base times height comes to a half. Or I can use symmetry, and I'll do that whenever I can to make my life easier. The total area actually is equal to 1. And I can see this graph is symmetric around 0. So below 0, I'll get half the area. Above 0, I get half the area. So I can use symmetry, and I can just get half straight away. If the total area is equal to 1, and below and above are equal in area, there must be half each. So either way, I get for this one here, probability 0 less than or equal to x less than or equal to 1, I get a half, or 0.5 if you wish. Next part says probability -0.5 to 0.5. Now here, again I'll draw the PDF. There's 0.5 and there's -0.5. So I'm after the area in the middle. Again I can use symmetry. So if I work out this area here, I can double that. So probability -0.5 is less than or equal to x is less than 0.5 is twice the probability 0 is less than or equal to x is less than or equal to 0.5. Now the area I'm looking at here between 0 and 0.5 is a trapezium. That's a trapezium. And the area of the trapezium is found by looking at the average of its parallel sides times the vertical distance, vertical height. Now this 0.5 there, you'll find this equation was -x plus 1. When x is 0.5, that looks like a 0.5 as well. So this height here is also 0.5. So my area should be twice the average of the parallel sides. The parallel side is 1 and 0.5. Over 2. And the vertical height here is also 0.5 or a half. And you can calculate that any way you wish. I can do, for example, cancel the 2's off here. 1 plus 0.5 is 1.5 or 3 on 2, and 3 on 2 half of is going to be 3/4. However you work it out, you'll get 3/4 of 0.75. There's another way of doing this problem here. I can, instead of working out the area in the middle here, I can work out the end bit. that n bit is going to be equal to a half. The base is a half, between 0 and 1 there. And the height is also a half. And that comes to an eighth. And so this side also of our symmetry also comes to an eighth. So I can say probability that I want here is 1 minus twice an eighth. And 2 times an eighth is a quarter. Again, I get 3/4. So all I'm using here is the geometry. And you should use the geometry in any way, as simple as possible, and do it cleverly if you can, to make your life easier. And so most of these kinds of examples that you'll see in here and in the exams and tests afterwards, and in problem sheets at this stage, will be based on geometry. Part 2. Part 3, probability x equals 1. This is simple. It's a single point, and we know probabilities for single points are 0. That's the end of that one. Part 4 is a bit more complicated. It says probability x is bigger than 0.5 given x is bigger than 0. So the first thing I do here is use my conditional probability formula. That says that I want the intersection of these two things. Probability x is bigger than 0.5 and x is bigger than 0 over probability x is bigger than 0.5. Sorry. Over probability of x bigger than 0, the given part. Now the intersection of bigger than 0 and bigger than 0.5 is simply bigger than 0.5. It's bigger than 0 and bigger than 0.5, it must be bigger than 0.5, and x bigger than 0. X bigger than 0.5, in fact I worked it out over here. It's 1/8. So that part's 1/8. And x bigger than 0 by symmetry was a half. And so here's some fraction work for you. Dividing by a half means multiplying by 2 over 1. That comes to a quarter. You can use decimals here if you wish, unless the question asks for the answer in fractions. That covers this example. Thanks. Bye.